put down whatever Arthur was rambling about yesterday regarding the sun. Tracking our local star is simple when you're sitting right inside its solar wind. The real flight downlink just synchronized, and we need to look at these numbers. I'm Nova. If this is your first time checking into the log, this console tracks real deep space telemetry. While Arthur covers our local planetary neighborhood, my station monitors hardware, optical sensor resolution, orbital mechanics, and the raw physics of exoplanets thousands of light years away that humanity cannot physically reach. Whenever news breaks that astronomers discovered a new Earth-sized world 20, 50, or 100 light years away, the initial instinct is to picture a deep space photograph. We imagine pointing a giant telescope and snapping a clear picture of oceans, continents, and cloud layers. That is not how this works. At those distances, our fastest chemical rockets would take tens of thousands of years just to arrive. Through even our largest ground and space-based optical mirrors, a distant star is nothing more than a single unresolved point of light, and the planet itself reflects far too little illumination to ever show up directly on a camera sensor. So how do we know these worlds actually exist? How do we calculate their mass, map their orbits, determine what they are made of, and figure out the exact chemical recipe of their atmospheres? We do not look for the planet directly. We measure the precise physical effects the planet forces onto its host star. The first fundamental technique is transit photometry, which powers orbital observatories like Kepler and TESS. Instead of taking pictures, these spacecraft use cryogenic charge-coupled sensors to count individual photons arriving from distant star systems. When an exoplanet's orbit lines up with our line of sight, it crosses directly between its star and our telescope aperture. As it passes, it blocks a microscopic fraction of the star's radiant surface. For a massive gas giant, that transit might dim the starlight by around 1%. But for an Earth-sized rocky world, the drop in brightness is tiny, roughly 0.01%. That is the optical equivalent of tracking a single mosquito flying across a car headlight miles away. By measuring the exact depth of that dip, optical physics reveals the planet's physical diameter. By tracking the precise clockwork interval at which that dip repeats, orbital mechanics gives us its exact orbital period, or how long its year lasts. The second major method is radial velocity, executed by ultra-stable, high-precision ground spectrographs like ESPRESSO. What happens if an exoplanet's orbit is tilted so it never crosses in front of its star from our point of view? In that case, the star never dims. But gravity still leaves a clear trail. A planet does not orbit the dead center of its star. Both objects actually orbit their shared center of mass, known as the barycenter. Because the planet exerts its own gravitational pull, it forces the star to execute a small rhythmic wobble in space. As the star wobbles slightly toward Earth, its light waves compress, shifting toward the blue end of the spectrum. As it wobbles away, the light waves stretch out, shifting toward the red. Our ground-based instruments can detect Doppler velocity shifts down to less than 1 meter per second, ruling the speed of a casual human walk in a star hundreds of trillions of miles away. By measuring the speed and timing of that wobble, we can directly calculate the planet's gravitational pull, which reveals its minimum mass. Once you have both methods working together, you have the planet's physical size from the transit and its mass from the wobble. Dividing mass by volume gives you density. That simple equation tells you if the planet is a solid ball of iron, a rocky world like Earth, a deep ocean planet covered in water, or a puffy gas giant made of hydrogen and helium. To take it a step further and analyze the atmosphere, observatories like the James Webb Space Telescope rely on transmission spectroscopy. During a transit event, while most of the starlight is blocked by the planet's solid surface, a razor-thin sliver of starlight filters straight through the outer layers of the planet's atmosphere. Before reaching the telescope's gold-coated beryllium mirrors, every chemical element and gas molecule absorbs very specific wavelengths of light. Water vapor absorbs one set of infrared frequencies, methane absorbs another, and carbon dioxide absorbs a different slice entirely when the telescope splits that filtered starlight through a diffraction grating. It creates a spectrum with specific missing lines, essentially a chemical barcode stamped directly onto the starlight. We never have to physically touch the atmosphere or send a probe into its clouds. The star's own light carries the chemical blueprint straight across interstellar space to our sensors. We did not just build machines to look at the stars. We built them so humanity would never feel blind again. What is the next mission you want us to track on the console? Leave your coordinates in the comments and hit subscribe to stay logged in. Telemetry synchronized, flight log stored, back to the console.